When we interact with a modern chatbot or watch a self-driving car navigate traffic, our first instinct is to assume there is a digital mind at work, processing information much like a biological brain. But look at the core definition on this slide. AI systems do not possess human intuition. They rely on an algorithmic infrastructure. What we perceive as cognition is actually a rapid execution of computational structures. Every instance of automated perception, every image identified, every sentence generated, is driven entirely by mathematical functions and probability distributions. When a large language model predicts the next word in a sentence, it isn't understanding the concept of language. It is calculating a probability distribution over an internal vocabulary list using multidimensional vector transformations. To actually see how these models work, we have to look past the chat interface and examine the exact mathematical frameworks that govern learning, prediction, and uncertainty. This interconnected landscape map shows that artificial intelligence is not built on a single isolated branch of math. We rely on linear algebra for data, calculus for change, and probability for risk. Think of this integration as a continuous production pipeline. Raw data enters on one side, passes through distinct mathematical processing stations, and exits as a trained model. Each station has a specific mechanical purpose: structuring unstructured inputs, identifying hidden relationships, and minimizing predictive errors. This pipeline is the exact blueprint we will follow to see how an AI model is constructed from the ground up. Computers cannot process raw audio, text, or images directly. Every piece of real-world information must first be translated into a structured numeric system. Linear algebra provides data containers for this translation. A digital color image is stored as an m by n by 3 tensor, representing red, green, and blue pixel intensities. Notice the linear layer formula at the bottom. The input vector x undergoes a rapid matrix multiplication with a weight matrix w. This single operation is the baseline computational building block for deep learning. But raw data is usually messy and divergent. Multiplying unstructured numbers directly would destabilize that equation. Here, statistics provides the necessary preprocessing. As the text indicates, data engineers use dataset standard deviation and mean metrics to scale divergent variables down to a unified, zero-centered distribution before the model even initializes. Before any learning can occur, linear algebra constructs the skeleton, and statistics ensures the inputs are clean enough for computation. If the system only sees numbers, we have to establish how it associates meaning between different concepts, like the words king and queen. This is achieved through embedding spaces. Categorical data is transformed into dense numerical vectors and plotted as specific coordinates within a continuous, high-dimensional space. This slide highlights the cosine similarity metric. Geometry allows us to measure similarity not by dictionary definitions, but by calculating the directional angle between two vectors, as shown in the formula here, regardless of their magnitude. Modern search engines and recommendation systems rely entirely on this mapping. Words with related meanings are positioned close together in the vector space, enabling accurate semantic matching. By converting text into points in space, the system turns human meaning into measurable Euclidean distance. Even with clean data and precise spatial mapping, real-world information is full of unexpected variables. Probability gives the model a framework to handle this noise. Instead of making a binary guess, it calculates a confidence score across multiple possible outcomes. Look at Bayes' equation on this page. This theorem is the logical foundation for updating a model's belief system as new evidence arrives. For example, a spam classifier evaluates specific keywords to continuously compute the conditional probability that an email belongs in the spam folder versus the inbox. To further evaluate these probability distributions, we incorporate information theory, specifically a framework called entropy, which measures the level of surprise or randomness in a dataset. This slide shows the entropy formula. Large language models evaluate their own text generation output by calculating cross-entropy loss, minimizing the randomness across vocabulary selections by summing up the probability of each outcome multiplied by its surprise factor. These probability and information frameworks ensure the model can operate accurately within the gray areas of unpredictable information. We now have structured data, precise spatial mapping, and measured uncertainty. The final requirement is an engine that finds the absolute best settings for the model's internal weights. We define a loss function to calculate the exact variance, the error distance, between the model's current prediction and the target ground truth data. This slide explores the challenge of navigating convex versus non-convex landscapes. During tuning, optimization algorithms must traverse complex, multi-dimensional error surfaces, seeking to locate the global minimum while avoiding local traps. To navigate this landscape safely, we use calculus. We take partial derivatives to isolate individual parameter effects, combining them into a multivariable gradient vector that points in the direction of steepest descent. This leads to the weight update rule shown here. The system updates its internal configurations by subtracting a controlled step size from the old weights in the exact direction of the calculated gradient vector. This chain rule isolates individual parameter contributions to propagate corrections backward through the network layers. In conclusion, artificial learning is a precise, multivariable optimization strategy, a mathematical navigation steadily stepping down an error curve. Theoretical math formulas are precise on paper, but executing them requires physical hardware with finite memory and processing limits. The core concepts here address those constraints. Computers cannot solve complex multi-billion variable equations exactly. Instead, numerical methods provide iterative approximation strategies, designing robust algorithms to prevent floating point limits from corrupting model weights. By factoring large matrices into simpler component parts, we speed up processing times across distributed GPU clusters. Numerical stability ensures the theoretical mathematics can survive the messy reality of physical computation. The integrated machine learning pipeline on this slide synthesizes the entire process. Data is structured using linear algebra, normalized with statistics, mapped via geometry, evaluated under probability, and iteratively optimized through calculus. Knowing how to import pre-built AI library code is useful, but true comprehension requires a firm grasp of the math driving those frameworks. As the final inspirational message states, to understand AI deeply, we must understand the mathematics behind learning, prediction, uncertainty, and optimization. You do not need to master every field overnight. Start by building solid foundations in linear algebra, calculus, and probability. Mathematics is the foundational language of artificial intelligence. Mastering it provides the map required to design, debug, and innovate the automated systems of the future.